Well, thanks folks for inviting me to give the colloquium today. It's a pleasure to be here. I was just trying to remember how long ago it was I last visited, and it was so long ago I actually cannot dredge it out of the memory bank. So I'm going to tell you today about ultra diffuse galaxies. I'm going to tell you what they are and why they're interesting. I have a bunch of collaborators. I used to work, as you heard, in California for most of my career. So I have a bunch of North American collaborators, and these are the folks I work with at Swinburne. So what I'll talk about is part of the project called Agate, and it's analysis of galaxies at the extremes. So you can tell that this is part of that portfolio. So I'll tell you what globular clusters are, because they're very key players in this story. I'll tell you why globular clusters are very important in understanding galaxy formation and evolution. I'll tell you what ultra diffuse galaxies are, and I'll tell you about the multiple types of ultra diffuse galaxies that appear to exist in our universe. Globular clusters, it turns out, are especially important for understanding UDGs, and I'll tell you why. I'll look at the comparison with simulations with observations, and then I'll tell you what I told you. So globular clusters, for those of you that don't know them, love them like I do, this is a globular cluster. So it's a star cluster, a spherical aggregate of stars, about 10 to the 5 to maybe 10 to the 6 solar masses worth of stars in a globular cluster. This is an artist's license showing a globular cluster orbiting around a galaxy. Almost all galaxies have some sort of system of globular clusters above a certain quite low galaxy mass. So there's a lot of reasons to think that globular cluster formation accompanies all the major star formation episodes in a galaxy's history. They're also very, very old, so as old as we can measure them. In fact, JWST results are indicating that they are basically the age of the universe, as the age of the first stars. So they actually act as bright fossil traces of all the processes that build the galaxies we see today. So all the mergers and acquisitions that build up a present-day galaxy, the globular clusters, once formed, don't change very much, and they're along for the ride for all these processes that build up a galaxy. And because you've got 10 to the 5, 10 to the 6 worth of starlight, they're quite bright, and they're very bright compared to the underlying starlight in the galaxy that hosts them. So we can do spectroscopy out to quite large distances. Now there are differences in the globular cluster systems of different kinds of galaxies. Giant galaxies, like the elliptical galaxies, can have very large numbers of globular clusters swarming around them, up to tens of thousands. Spirals, like the Milky Way, only have a few hundred maybe, and dwarfs can have none. Dwarf galaxies, so they're these little guys with not very much starlight, to maybe a handful, less than a dozen. So that brings me to ultra diffuse galaxies, because I wanted to explain to you why globular clusters are so important for understanding these things. So this is Andromeda, our sister spiral galaxy. This is an ultra diffuse galaxy. So these pictures in this collage are all on the same scale. So this is a dwarf elliptical galaxy. This is a dwarf spheroidal galaxy. And these two have the same effective radius, the same half-light radius. So ultra diffuse galaxies have a working definition, very low surface brightness, and sizes bigger than 1.5 kiloparsecs. So these guys have the starlight of dwarf galaxies, but the sizes of giant galaxies. So we've only been talking about ultra diffuse galaxies since 2015. and I'll tell you why. But as a bit of history, low surface brightness with this relatively arbitrary definition have been known about much, much earlier than 2015. A handful, just literally a handful, have been known about since the 1980s. But it wasn't until they were identified in large numbers, thousands, in the Coma cluster, the cluster of galaxies called Coma, that they were recognised as a new class of object. So just to put things in perspective, this is surface brightness against effective radius, so size. These are all galaxies in the Sloan Digital Sky Survey, so a big survey that's been going on forever. And these are dwarf galaxies in a relatively nearby cluster of galaxies, the Virgo cluster. And these are ultra diffuse galaxies shown in red. So this green line is the night sky. So these objects are on average 100 times fainter than the night sky. So right away you can tell this is a real issue for trying to find out more about them. Not only have they been found in clusters of galaxies, so dense environments, they've also subsequently been found in groups and also in the field, so not near anybody else, not near any other other galaxies. So the reason they were discovered was due to work by Peter van Dokkum and Bob Abraham. This is Bob Abraham at University of Toronto and Peter's at Yale. They, between them, literally at a pub, talked about putting together a whole array of off-the-shelf cameras. These are Canon cameras with with proprietary anti-reflection coatings, and they started surveying the sky. This covers a large area. It is now much bigger. This is an early photo. The array has been expanded and so on. Anyway, because this was optimized for low surface brightness objects, they started to discover these things, which, you know, on an image look just like a smear. The technology was finally good enough to start seeing these things, which we really didn't know were there in any numbers before. So you find something that's a new class of galaxies. What's the first thing you want to do? The first thing you want to do is measure the mass, or certainly one of the first things you want to do is measure the mass. So how do we do that? Well, you can look at the way the stars move in the galaxy and get a velocity dispersion. That gives you a mass estimate. This is extremely telescope time intensive. The one galaxy we've really done this properly has probably had about 20 to 30 hours on the Keck 10-meter telescope, which is, you know, basically the world's largest and most sensitive instrument for doing this stuff. So you can't develop a sample this way. You could, of course, do things like weak lensing, but there basically aren't any results for ultra diffuse galaxies, not detected in the X-rays. But happily, many of these ultra diffuse galaxies have quite large, and sometimes extremely large, globular cluster populations. So if you have globular clusters, and you can see some globular clusters identified in these images of different ultra diffuse galaxies, you can use their motions to deduce mass. The other thing you can do, a double bonus with globular clusters, is you can simply count the number of globular clusters associated with the galaxy. And the reason that works is because of this relationship that's been known about actually for quite a long time. This is the most recent rendition of it from Burkett and Forbes, where you see there's quite a tight correlation between the number of globular clusters and the halo mass of the galaxy. So when I talk about halo mass, I basically mean the total mass of the galaxy. And that's typically for massive galaxies at least, dominated by dark matter. So total mass against globular cluster number, and there's a tight correlation. And this is an ultra diffuse galaxy, this one I mentioned that has been the best studied so far. It seems to know that it's supposed to lie on this relationship. So if you can count globular clusters, you can infer a total mass for the ultra diffuse galaxy, even though you don't have a hope of getting that from the velocity dispersion of the relatively faint starlight. So just to illustrate some of the problems we have with theorists, sorry, probably half of you are theorists. Not theorists, theory, not theorists. Theorists are lovely. It's theory that's the problem. So here's ultra diffuse galaxies in red. There's some dwarf ellipticals in green. There's dwarf irregulars there. This is stellar mass against halo mass. And you can see the region here. I'm going to highlight the region in which the globular clusters lie above some sort of canonical halo mass stellar mass relation. So they lie high. Now, unfortunately, in the next figure, the axes are swapped. I don't know whether to blame the theorists or the observers for that, but they tend to be swapped. And this is now stellar mass against halo mass. But what I want you to see, and this is from simulations, this plot is from simulations. This happens to be the Romulus C cosmological hydrodynamical simulation. I'm wondering where I put my water. Oh, there it is. I tucked it away carefully and then forgot where it was, so excuse me. A bit croaky. So that's where those observations were. So you can see that these simulations, at least, don't reproduce the area that we're finding ultra diffuse galaxies. So these lines are just the canonical stellar mass halo mass relations from various authors. Ultra diffuse galaxies from the simulations are the orange ones. So there's no simulated ultra diffuse galaxy where we predominantly find the observed ultra diffuse galaxies. So let's have another look. So there's another interesting relationship, which is also quite well known. There's this curved shape when you plot mass to light ratio against mass. And over here, we've got ultra diffuse galaxies where their positions have been determined from globular clusters, and in some cases from stars, where we've had to lean quite heavily on the observations. So you'll see that most of these ultra diffuse galaxies are lying well above this relationship. And if you look down here, and there's a couple that are low, I'll come back to those in a minute. But you can see that there's very extreme variations in the mass to light ratios of ultra diffuse galaxies. So we have to understand that if we're trying to understand where they came from. So this is the same thing, but the FIRE simulations. FIRE is a suite of simulations that are particularly looking at dwarf galaxy formation. And you can see that they can reproduce some ultra diffuse galaxies, but certainly are nowhere near reproducing many others. Okay, so I want to tell you that I'm going to make a statement, but it's pretty well supported. I'm talking here about ultra diffuse galaxies that are old and gas poor. So there are things that satisfy this criterion, this arbitrary definition, that are gas rich in the field. I'll mention those later, but that's not what I'm talking about. I'm talking about the ones that I think are particularly interesting. So there are three basic routes, three basic classes of ultra diffuse galaxy. There are puffy dwarfs, so these are the dwarf galaxies, like I showed you at the beginning, the little guys, that have been puffed up by some mechanism and made ultra diffuse. So they're basically just puffed up dwarf galaxies. You can do this with tidal interactions. There are theories which use that say they're the high spin tail of galaxy distributions. You can potentially do it with strong feedback, meaning as the stars go through their life cycles, they throw out lots of energy and can puff up the ordinary dwarf. So if you're looking for these things, you expect modest halo masses, typical of dwarfs. By halo mass, I'm talking about the dark matter in which galaxies are generally embedded. Low velocity dispersions, indicating low mass, and very few globular clusters. Failed galaxies, on the other hand, which is what got me interested in this area, have large halos, dark matter halos, typical of a giant galaxy, like the Milky Way. They appear to have formed stars early, but ceased subsequent star formation. Why? We don't know. People have written papers about doing this with tidal heating, ram pressure stripping. So if you chuck a potential giant galaxies coming into a cluster of galaxies, it gets all its stuff stripped away, and it can be puffed up. That doesn't help you if you're trying to explain the ones that are in the field, of course, because they haven't fallen into a cluster of galaxies and therefore haven't had the opportunity to be ram pressure stripped. So you can also invoke an early phase of star cluster formation, which makes very massive star clusters early on, and when they go belly up, they reach the end of the massive star life cycle, they eject gas and puff things up, but it's extremely hand wavy at this point. Nobody's really got that sorted out at all. But if you're looking for failed galaxies, you expect high halo mass, so high mass galaxy, high velocity dispersion, if you can measure it, and lots of globular clusters. So these are the interesting ones, and these are the ones that really aren't reproduced in simulations. There are also dark matter-free ultra diffuse galaxies, and those weren't expected at all. But I'll come back to those in a minute. Okay, so let's see, how am I doing for time? Did I start at 2? About 10 past 2, okay, good. So I know. Do I still have to end at 3 or 2:45, or when am I end?
Probably start taking questions at 3 in case people have.
Oh God, yes, yeah, that's fine. I thought you might want me to stop earlier. Okay, so there are globular cluster-rich galaxies, ultra-diffuse galaxies like this one. You can probably see there's lots of little points here. These are all globular clusters. And there are ultra-diffuse galaxies with very few or none. So we speculate that the failed galaxies are the globular cluster-rich ones, and the puffed-up dwarfs are the globular cluster-poor ones. But as I've mentioned, you get both types in all environments. And many ultra-diffuse galaxies have remarkably high specific frequencies. And all that means is they have loads of globular clusters per galaxy starlight, or indeed per galaxy mass in some cases. So that's the problem in a nutshell. We know some more things. Globular cluster poor ultra-diffuse galaxies live in undermassive halos. So this is work led by my postdoc, Jonah Gannon. The mass here within a radius against radius, and these are different masses of the parent galaxy. of parent galaxies in general, and the red points, squares, are globular cluster rich UDGs, and the blue ones are globular cluster poor UDGs. These are just different models of the dark matter halo, whether it's cuspy or chord. That actually does matter because it feeds into our cosmological simulations. But in this case, all I want to tell you is that the globular cluster poor galaxies live in much lower mass dark matter halos. So that's important. And because that is true, that fits in with our sort of general understanding that galaxies formed at earlier redshifts are expected to have more globular clusters. So that's been talked about quite a lot in the literature. At higher redshifts, I mean, this comes out of lambda CDM. At high redshift, halos are more compact and the core mass is higher. So that's the dark matter distribution. So you actually have an expectation of a correlation between the richness of a globular cluster system and the dark matter mass, which we see here. Okay, so I think I've probably gone through the reasons why we want to use globular clusters in understanding UCDs. The problem with using globular cluster formation, using globular clusters, is we have relatively poor understanding of globular cluster formation. And obviously, you've got to explicitly simulate it, and most cosmological simulations, in fact, almost all of them, don't simulate the globular cluster formation, and that's just because it's too difficult. You know, you don't have enough computer power. But there's a hybrid approach which is called emosaics, which has a cosmological hydrodynamical galaxy formation simulation called EAGLE, which gives you hydrodynamics and stellar evolution, gives you enrichment, mass loss, and various other parameters for the galaxy. And you can feed this into this subgrid model, mosaics, which is specifically to understand cluster formation and evolution. So on the fly, this model at all different time steps simulates globular cluster formation dictated by cluster physics and the local environment. So you don't need to know all the details here, but out drops the globular cluster population at whatever time step you're inquiring at. So I'll just show you that. Hopefully it will go. Maybe it won't. Well, what you're going to see in a minute is this simulation, again led by Joel Pfeiffer, my postdoc. And it starts at redshift 20, goes in 0.2 gigayear time steps. And on the sides here is the globular cluster metallicity. So the purple things are low metallicity, yellow things are high metallicity. Excuse me. See if I can get it to go. Yes, there it goes. So this looks like a cosmological simulation. You've probably all seen those before. But the lights now, the colours and the lights, these are globular clusters forming. So each star particle in this hydrodynamical simulation contains a globular cluster. So this build-up of the galaxy is producing globular clusters, and you can see as the simulation finishes, you'll see that the metal-rich globular clusters, these orangey colours, relatively metal-rich, wind up predominantly in the centre of the newly formed galaxy, but the metal-poor ones, the metal-poor ones, by metals I mean everything more metal-rich than hydrogen and helium, that's just how we refer to it, The metal poor ones are slung all over the place. Okay, so we got a simulation finally that we can compare to observations. So this is recent work that Joel's published. So what you're looking at here is a simulation for objects of dwarf galaxy mass. So these are not necessarily just ultra diffuse galaxies, they're galaxies with low mass. Dynamical mass on the sides here, and in full redshift. This just really means the redshift at which we call it the infall line. So that means the place when the galaxy fell into the next largest massive agglomeration. So you can sort of think of it as formation. So we've got high specific frequency, this is this SM thing. It just means globular cluster rich in red, globular cluster poor galaxies in blue, and you can see that the globular cluster rich ones mostly had early infall. So they started up here and then they got stripped when they went into another environment. And so their mass got decreased. And then globular cluster poor UDGs fell in later, or not at all. They haven't fallen anywhere. They're just in the field, and they tend to have higher mass because they haven't had much stripping yet. They haven't had any interactions with their environment yet. So that's kind of the story. Now, how does that jibe with the observations? Well, here's some observations of globular cluster rich galaxies. And what you have to think, so this is like a big error box, but these error boxes are quite small. So you have to think about, we don't know when these things fell in or when they formed. So you can slide this along here somewhere. It can be anywhere along here in principle because we don't know where they formed. But you can see, okay, well this is reasonable. This guy, there's a range in enclosed dark matter for globular cluster rich simulations, which is roughly equal to what you see. You can imagine this one is over here, probably fell in at this redshift, for example. I mean, kind of looks okay. But if you put the globular cluster poor ones on here, it doesn't work at all, right? You can slide these backwards and forwards all you want, and it's very, very hard to get the blue ones to match up with any of the simulations. So I think this just means there's a lot of stuff we still don't understand. There's a flaw in these simulations, meaning you can't produce the full range of expected properties of globular clusters, and there's a new version of mosaics called Calibre that will address these temperature flaws and velocity flaws. Anyway, oh, wait, did I miss something? Yes, I did, just a sec. I missed a lot. Oh, how did I do that? Okay, so I jumped. Let's not jump. So globular cluster rich versus globular cluster poor. Why? What makes what's the difference? And these simulations suggest that it's the natal gas pressure. So the idea is you get high gas pressure when the object is forming, at relatively high redshift, early times, high star formation rate, density because of high pressure in the gas, and you form a lot of globular clusters in circumstances like that. And so this is what this is showing. This is the number of globular clusters per unit galaxy mass, and it's trotting up here as you would expect. And above some mass, pressure, you have very large numbers of globular clusters formed. Then you can say, how does that translate into stuff we might be able to measure? So this is the prediction from the simulation, is that more dispersion supported, higher velocity dispersion for galaxies with higher gas pressure. Galaxies with lower forming when the gas pressure when they formed will be diskier. And this doesn't work out quite as well on the face of it. And this is you have, but the issue is you have to take into account the inclination of the galaxy. So if a galaxy's face on, this is what the simulations predict. So this velocity dispersion, globular cluster rich ones have high velocity dispersion as suggested. And then if you take inclination into account, it smears out this relationship, so it doesn't seem to work very well. This is all galaxies at various different rotation angles of inclination to the observer. But happily, it is still true that the ones that have very high globular cluster counts are in this region up here. So we do expect the ones with few globular clusters to be diskier, and the ones with lots of globular clusters to be rounder. So that's a prediction. Yay! Finally, observers get a proper prediction. More rotation in globular cluster poor, ultra diffuse galaxies, rounder shapes for the globular cluster rich ones, and of course, since this is not just a simulation for ultra diffuse galaxies, it applies to all dwarf galaxies. So what do we know? We know some things, but not very much about rotation. So it's very difficult to get the rotation measurement, especially if you don't have any globular clusters. So you kind of have to resort to objects which have gas in them, which are not necessarily the same things. So this is some work done on the number of globular clusters. It was actually a compilation by Jones against the absolute magnitude, the absolute brightness of the galaxy. And everything on here is an ultra diffuse galaxy. And these black ones are ones in which the H1 measurements have shown that the galaxy is rotating. Now, all of these have very, very low globular cluster numbers. There's only one properly explored globular cluster rich galaxy, DF44, which we have explored its starlight properties, not its globular cluster motions. Well, we've done both, but the point for here is it isn't rotating and it has lots of globular clusters. And all of the gas-rich field ones, where we can measure rotation, they are rotating and they don't have very many globular clusters. So another thing we've learned, even though this is all consistent with the predictions from the simulations, the gas-rich field UDGs are not ever going to be the progenitors of the globular cluster-rich UDGs, the ones that I find the most interesting. They're over here. These are simulations in purple and in orange. These are simulations. These are the observations of gas-rich field UDGs, and there's no way these things can evolve to have higher halo mass and more globular clusters. They don't have very many globular clusters. as you can see from here. But they certainly could be the progenitors of globular cluster poor UDGs. So maybe that's the formation pathway for the poor ones. So let me, there's an elongation question. So again, the prediction from the simulations is that the globular cluster poor UDGs are diskier. So what is that borne out by, because they're rotating, is that borne out by observations? And the answer is yes. So ultra diffuse galaxies with lots of globular clusters per unit, whatever you want to measure in the galaxy, they are the red ones, and the globular cluster poor objects, galaxies, ultra diffuse galaxies, are in blue. So there's a tendency for them to be diskier. Same is true for more recent work. This is also from my postdoc, Steve Janssens. He's now moved to Canada. This is results from the Perseus cluster of galaxies. And this is the number of globular clusters and the axis ratio. And over here are the high globular cluster count UDGs. And so even though this has this spreading that you expect because of the changing inclination angle that we view things on, it is true that all the high globular cluster count galaxies are all round, and all the elongated ones have low numbers of globular clusters. So it's just, it's starting to hang together a bit. Okay, last sort of section, and so I think I have time to do this. Well, actually, there's another one as well about the. We'll see how we go. I can always stop. So this is some work by my PhD student, Louisa Buzo, who has been using spectral energy distribution fitting. This is using photometry basically from a whole range of filters across a wide range of wavelengths, from the ultraviolet through to the infrared from the WISE satellite, the infrared observations. Okay, so this is some fitting done for a survey of dwarf galaxies called MATLAS. So what you've got here is metallicity and stellar mass. The yellow is all galaxies, giant galaxies from a compilation by Galaxy, and the purple and the grey are two different bands of dwarf galaxies. This one is from Kirby. This is basically local group dwarf galaxies, and this is the Simon one, is a bigger group. Now I want to point out this relationship here is from Ma et al. It's the relationship between metallicity and stellar mass at measured at a redshift of 2.2. Now, this is globular cluster number in blue. So the red ones have the highest globular cluster count per unit galaxy mass, light, what have you. And the low globular cluster number ultra diffuse galaxies lie pretty solidly in the dwarf galaxy area, so normal dwarf galaxies. And these ones, the grey things, don't have any measurements, so we don't know. The high specific frequency, high globular cluster richness, seem to be way below this dwarf galaxy relation, and perhaps more in line with the high redshift version. If you look at that with a bigger sample, this is not just the field and group dwarfs that I just showed you. This is all environments. You can see this trend is emphasized. So the red ones, again, seem to correlate with the relationship at relatively high redshift, and the globular cluster poor things again, look very much like ordinary dwarfs. So we speculate that they've been puffed up, but we're struggling with this lot. How do we form these? So again, looking at the predictions, this is axis ratio here. So these are the round guys, these are the very disky guys. And again, you see that those same objects that we were looking at that are globular cluster rich, they are also they're round, generally, rounder, and seem to like to congregate on this high redshift line. So lastly, star formation timescale can be modelled with these CECD fitting algorithms. So again, star formation timescale, these things down here, these are the ones of interest. Short star formation timescale. So early formation, short formation timescale, low metallicity. This is low metallicity down here, which tends to make you think they were formed earlier when the universe wasn't as enriched with metals, and look like they want to follow a much higher redshift relation. So the opposite, of course, for the other objects that are what we're supposing are the puffed up dwarf galaxies. Okay, so last bit of this, just to emphasize, Louisa came up with this diagram which helps emphasize that when you take in all the parameters that you can measure and observe, and this is for 37 ultra diffuse galaxies, all of which have their globular cluster numbers counted, you can do this grouping algorithm called k-means, and you get a clear separation into two classes. So the green ones are this low stellar mass, more metal rich, more elongated, longer star formation history in less dense environments, fewer globular clusters, younger, fainter, smaller, and look like classical dwarfs from their the fundamental stellar mass metallicity relations. Opposite is true of group B, which is of course the more massive, more metal poor, short star formation timescale, rounder, in the densest environments, richest globular cluster systems, etc., etc., etc. More like the mass metallicity relation at high redshift, and so consistent with something that quenched the star formation early. So the idea is that the galaxy started out as a proto-normal giant galaxy, formed its globular clusters, and then, before it could form very many stars at all, something quenched it. Lastly, and I have probably just a few minutes, I thought it would be nice to tell you about the ones that we didn't expect at all, the ones that don't have any dark matter. So this is a conundrum as well. Started out with two of these objects. I like this because it's all these acronyms. So UCDs, the UCDs are ultra compact dwarfs in ultra diffuse galaxies, UDGs, lacking dark matter. And I'll tell you what UCDs are. So if you, in recent, maybe 20 years ago, ultra compact dwarfs, maybe longer, I don't know. I'm so old, I don't remember these things. The ultra compact dwarfs were discovered, and they're like big globular clusters. So they're too big and too bright to be globular clusters. And there's an ongoing debate about whether they're the stripped nuclei of ordinary nucleated dwarf galaxies, or whether they're formed by some other process like merging globular clusters. That actually doesn't seem to work very well. But anyway, we don't exactly know what they are, but they're big star clusters, which are too big to be called globular clusters. Okay, So there's these two ultra diffuse galaxies that were discovered in the 1052 group. So this is a group of galaxies, and two of them have, you know, they're very faint ultra diffuse galaxies with a bunch of star clusters around them. But when you actually observe these star clusters, they're really, some of them are really bright. So here's a normal globular cluster luminosity function, and it's at the right peak and it's got the right width for normal globular clusters. And then there's this lot that are too bright, and it turns out they're also a bit elongated, so they might be stripped nuclei or what have you. So in these galaxies, if you look at the motions of all of these things, surprise, consistent with no dark matter. So very different from the other ultra diffuse galaxies I've been talking about. Very narrow velocity dispersion, which is consistent with no dark matter. So we're not on the edge here. This is a pretty clear result. So a lot of controversy about this, tons of papers saying, you know, the distance is wrong, this, that, and the other. But I think it's pretty solid, actually. So nobody has been able to figure out how to produce these galaxies with no dark matter, all these globular clusters, and particularly all these really bright star clusters. We can call them UCDs, ultra-compact dwarfs, but whatever they are. So Peter had a Nature paper in which he proposed a scenario, really, it's not even really a model, where you basically have two gas-rich galaxies that collide. And it's called the bullet dwarf formation scenario because it's like the bullet cluster idea. So you have one progenitor going round in the NGC 1052 group, another gas-rich thing comes in, they collide, and that process creates a trail of UDGs in a trail that are stripped of dark matter. So this is the DF2, which is one of these dark matter-free galaxies, and DF4 up here, those are, oh, sorry, DF4 is there, that's the other, the progenitor of the other one. So they are at opposite ends, I was right. So DF2 is here, DF4 is there, they're the two that we know about and have measured. And then the remnants are kind of at the end of this trail. So this is just a hand-wavy scenario. It is based on some earlier work that did a fairly careful study of a similar scenario. The good news about this is it's the only model or hypothesis or scenario where massive star clusters are actually made, because they're made in this gas-rich collision, and that's how you make massive star clusters. So to explore this further, we spent lots of Keck time looking at the stellar population, so the ages and metallicities of these objects. So if this scenario is right, these things should have the same stellar population, same ages and metallicities. So they do, so that's good. The supposition is that this collision happened about 8 gigayears ago, and we do get that age in both of these things. Now, needless to say, what you want to do is then look at all of these. I should say, on the images, there is a trail of blobby things, but they're fainter than these two, so it's really hard work. So we have some nights coming up soon. Peter has 3, and I think I have 2 coming up. So we're going to try and hammer on some of the ones that, maybe we can get some headway on determining that. Okay, so that's a kind of, it's a scenario that may or may not hold water. But interestingly, we found another one, and this is just my last bit. We found another dark matter-free ultra diffuse galaxy, and it's in the Fornax cluster. It has an age of about 10 gigayears, relatively low metallicity, and it has, see down here, has 6 confirmed globular clusters. There are probably more, right, because there's loads of little blobbies here, but these are the ones that have been confirmed. These globular clusters all have basically exactly the same colour, and it's the same colour as the galaxy, starlight. So that suggests there was a single burst of star formation that formed the galaxy and the globular clusters. And just like those other two, DF2 and DF4, DF stands for dragonfly, that array of cameras that I showed you early on is called the dragonfly array. So the things it's discovered are called DF something. So DF2 and DF4, these galaxies have this top-heavy luminosity function, meaning these ultra-compact dwarf objects that are too massive to be globular clusters. And this guy also has them, top-heavy luminosity function, and also very low velocity dispersion of both the stars and the globular clusters, consistent with no dark matter. So I think we're good there. This is, there are some differences between this galaxy in Fornax and these two group dark matter-free objects. In this case, the globular clusters are very centrally concentrated. That's not true for these galaxies, nor is it true in general for UDGs. It's usually this half number radius is about 1. In this case, it's 0.5. The globular cluster, the massive ones, are not extended, so they're not big like ultra-compact dwarfs. And there's no massive galaxy nearby, so we don't know if that's a requirement. But so far, the bullet dwarf scenario is still the best one, because how else do you form the very high mass star clusters? Okay, so that's good. We haven't published that. That's hot off the press. Both papers are now submitted. So now I can just tell you what I've told you. There are 3 distinct types of old metal poor globular clusters: puffed up dwarfs, failed galaxies, and dark matter-free galaxies. Happily, many of these failed galaxies have very large globular cluster populations. So we know that some of these UDGs are dark matter dominated. We know that based on the number of globular clusters, the dynamics of the globular clusters, where we can measure it, stellar velocity dispersion. But there are 3 that have no dark matter, strange overluminous star clusters, which might be ultra-compact dwarfs. So we think this phenomenon might be linked to high-velocity mergers of gas-rich galaxies, for want of anything better to compare to. So simulations actually can reproduce the puffy dwarf guys, the low globular cluster count ones, and there aren't any simulations that produce all of the characteristics of the failed galaxy class. And in fact, eMosaics, which does very well with the globular cluster rich dwarf galaxies, is still struggling with globular cluster poor galaxies in that particular simulation. So it's a bit of a mess on the simulation side. However, we do seem to be confirming that globular cluster poor galaxies are diskier and globular cluster rich ones are rounder and presumably formed and fell into their potential well, their galaxy potential well, earlier. So the SED fitting technique is a promising one because you don't need quite the signal to noise that you do for spectroscopy. It's getting a lot of basic parameters for these things for large samples, and we can see a clear separation in multi-parameter space between the globular cluster rich ones and the globular cluster poor ones. So when somebody says to you in your, at your next cocktail party, all UDGs are just puffed up dwarfs, you can say, no, they're not. Just heard a colloquium that clearly says that that's not the case. So we're working with mosaic simulations because they are the ones that are trying to simulate globular cluster formation in a cosmological context. So we think the globular cluster rich UDGs form early and fast, have lower metallicities because they're forming earlier, and they're pressure supported. The globular cluster poor ones have ongoing, in some cases, but certainly extended timescale star formation, higher metallicities, and they're diskier. And that's the story. Thank you for your attention.
You show lots of plots with distributions of where you have these different galaxy populations and so on. And at the same time, you talked about how difficult they are to actually find these here. So how much uncertainty do you get from various selection effects that you don't actually understand? You show populations sitting in different areas, but is that really dominated by the selection effect rather than by the physics of the formation?
Well, that's a really good question. And yes, we are worrying a lot about the selection because we are, the technology is only allowing us to go down to a certain faintness, right? So we're definitely dealing with that bias. Most ultra diffuse galaxies have been observed in clusters of galaxies because that's where they are in large numbers. So we have very poor statistics in the field, like just very few. So one of the goals of the DP I have is to explore the field and try and find out better what the statistics are there, and also we know a lot more about the globular cluster rich UDGs just because you've got the blinking globular clusters and you can see them and you can get a spectrum. The globular cluster poor ones, not so much, because we have to rely on starlight, and you try getting the time assignment committee to give you nights to look at a smudge where it might not be very interesting. So, and there's also another selection problem, which I think might be the most easy one to push on, and also the most revealing of formation pathways, which is that this definition is really arbitrary. I mean, it has no physics in it at all. So what we're calling, I came up with a clever name for the things that have just escaped being classified as ultra diffuse galaxies. So they're near the edge of this arbitrary parameter space, and it's particularly easier to go brighter. So we're going to go with ones that are just slightly too bright to be ultra diffuse galaxies. That's the next thing. But yeah, I mean, it absolutely is a problem.
Really interesting, thanks.
Thank you for the nice talk. So I just wanted to kind of summarize wanted to recap on all the correlations. So the rounder ones have more globular clusters, the less rounder ones have less, and the more rounder ones are more lower metallicity.
Yes.
So if I put this together, let's just try and put this in my head. So lower metallicity means less cooling, therefore you maintain the entropy and keep it round, and you have less disk shear, and then the shear, because you have less shear, don't break up the molecular clouds that form the globular clusters. And is that the kind of...
Yeah, that sounds reasonable to me, but there hasn't been much discussion of the actual physics of all of this. This is sort of phenomenological. This is what we've we've discovered, and we're trying in our crude observer way to try and link this to some deeper understanding of the formation processes. So yeah, please keep thinking for us, because it's quite tricky, right? Nobody's actually managed to form a globular cluster in theory yet. We don't know how to form a globular cluster, so